Hey everyone, I'm Bo Ingram, author of ScyllaDB in Action and staff engineer at Discord. I work on databases there on our persistence infrastructure team. I'm here today to give a talk I've entitled So You've Lost Quorum, Adventures in Accidental Downtime. But first, I mentioned I'm an author, so therefore I have to plug the book. I'm obligated to. ScyllaDB in Action is my favorite ScyllaDB book. So to learn Scylla, you learn how to run it and operate it, both from the perspective of a developer and an operator. I've got this awesome code here, CTW ScyllaDB. We'll link it in chat. It'll give you 45% off through May 15th. You can purchase it at manning.com, where it's in early access. It'll be fully released later this year. But I'm not here just to talk about a book. I'm here to tell about an outage. So many talks are about successes. We completed this migration. We can handle this much traffic. We've built this novel solution. And those are amazing talks. They bring value, new perspectives. They show capabilities. They're really great. I'm really looking forward to hearing some of them over the next couple days. This is not one of those talks. This talk is about a stressful Monday. It's about a ScyllaDB cluster that we run at Discord that had a bad time. So today, I want to look at a real-world Scylla incident. I want to take a look at how the database behaves when things aren't going great. And I also want to share 7 tips for Scylla Sev success. Did I remove one tip to preserve the alliteration? I'll never tell you. All right, Scylla authentication. That's the name of the database. So at Discord, we have a common problem for most web applications. We need to authenticate users' requests. So requests come into our API, and we need to validate the user that sent it. To do this, we send a request to our authentication service, which reads from our ScyllaDB, Scylla authentication. It's pretty standard for us. It runs our typical storage topology, which I'll talk about because it's very relevant for this incident. So we run in GCP, and we've got really 2 options to run disks. We can use local NVMe SSDs or Google's persistent disks. Now, NVMe SSDs are very fast. They're attached directly to the instance. But running them, we've observed low reliability. We see frequent bad sector reads, which is not what we want. Additionally, because they're attached directly to the instance, if we change instances, if there's a host error or we stop the instance, there's the potential for data loss because GCP needs to migrate that data to another set of NVMe SSDs. The other option is persistent disks, which sound pretty cool. I mean, they are persistent. The downside is they achieve that persistence through being network attached. So they're slow to read from because you've got to pay a small network cost. GCP is able to easily migrate the data though, so they persist data through instance changes because it's able to reattach through the network. So GCP says we got to pick one. We say we could have both via the power of Linux. So I talked a little bit about this last year, but we developed this hybrid RAID superdisk that gives us the best of both worlds. I'll talk about it pretty briefly here, but we have a blog post that goes into greater detail if you're interested. So we start with our local NVMe SSDs. We stripe them together with RAID 0, which A, masks the bad sector reads, but also B, gives us more than 375 gigabytes of local NVMe SSDs on a node. We then take the persistent disks and mirror it with those RAID 0 local SSDs via RAID 1. So it duplicates data to both the NVMe SSDs and the persistent disks. We mark the persistent disk as write mostly, which means the writes go to the persistent disk, but the reads will be served from the speedy local NVMe SSDs. This works great. It's good, it's performant, it gives us everything we want. It does have one big drawback: rebuild times. So when an instance starts up for the first time or starts up with new local SSDs, it's got to sync data from the persistent disk over to the local NVMe SSDs. This can be quite a timely procedure. For our authentication cluster, it'll actually take about 45 minutes. So a newly started authentication instance has to do a process for 45 minutes before it can actually start Scylla and accept traffic. This is going to be relevant later. So we have this hybrid RAID superdisk, and that describes our disk topology. But for the cluster itself, we run with a replication factor of 3 across 3 zones in our cloud provider. We design our instance topology to tolerate zonal failure. We want to be able to handle the loss of an entire zone. So we're running 2 nodes in each zone at the time of this incident for 6 nodes total. So that's our authentication cluster at a high-level overview. Let's talk about what went wrong, why it had a bad time. Now, before we dive into it, I want to give a quick disclaimer. You hear authentication incident, it sounds really scary, but this is not a security incident nor a correctness incident. Only availability was impacted. All right, so November 3rd, 2023, last year, a few months ago, we're performing an OS upgrade. So our plan is this. We're going to take a cluster zone, one zone at a time offline. We'll detach the persistent disk from it so it stays around. Then we'll spin up a new cloud instance with the new OS version. We'll wait for the RAID array to rebuild because it's going to get new local NVMe SSDs, wait for the nodes to come back online, and check that the cluster is healthy. So the zonal upgrade part of it is interesting. There's a balance here between speed and safety. It's an expedient way to perform database operations because RAID rebuild times for us can be very long. On our largest cluster, this can be 3 hours. You don't want to spend days, almost even weeks, doing a simple OS upgrade. And additionally, tolerating zonal loss is the goal of our topology. We design our clusters to handle zonal failover. And doing this operation zonally gives us an excellent chance to verify that we're meeting our goals. But there's risks, right? By taking an entire zone offline, there's no additional margin for error. So if we happen to lose a node in, say, B while C is down, we can have a bad time. Additionally, during this, the cluster is going to be running at 2/3 capacity. So you have less resources handling the same traffic as today. Because of the RAID rebuild, when this happens, you're kind of in this 45-minute danger zone, right? Where because you're waiting for the RAID to rebuild, you can't just bring them back online. You're stuck waiting. So this kind of like weird Bermuda Triangle, right? Of this 45-minute danger zone. All right. So November 6th, 2023, 3 days later. It's been successful so far. We've done hundreds of nodes successfully, and we've upgraded many of our critical clusters. All but 2 are left. Our messages cluster and our authentication cluster. So we start with authentication, obviously, because this is also the subject of the talk. But we know we hadn't zonally restarted it in a while. Like, okay, well, we want to make sure that this is a success. So let's not just start it and do the RAID rebuild and see what happens. That doesn't sound very exciting, right? Well, it sounds exciting, but not very fun. So we do a practice run. We do the good old no tool drain, stop Scylla, leave it offline for about 15 minutes, and it looks great. Latency is great. There's no errors, no application effects, no compaction backlog. Scylla looks great. Okay, we're confident. It's looking great. Let's begin the procedure for real. So 9:16 a.m., we begin. I've always loved this XKCD here. Things are about to get bad when the incident report starts including seconds in the timestamps. Well, we're not going to get to seconds precision, but we are increasing the precision of the timestamp and putting it in minutes. So the procedure begins against authentication, beginning with taking zone B offline. But we see this weird thing. We see a slow RAID rebuild on B2. One node is taking twice as long to resync its RAID array. This is new behavior to us. We haven't seen it before. Well, we talk about it as a team. We're okay, we do a health check at the end of every zone. So we can see what the health check says. And the health check's going to check all nodes are up. Latency's looking good. There's no compaction backlog. And so the RAID rebuilds and we get to that health check. And it runs and it says, hey, latency's looking good. No compaction backlog. All nodes are up. Things look safe to proceed for me. So at 10:52, we drain connections from zone Z and an outage begins. So this leads us to our first tip. Losing quorum is bad, and you should do everything to avoid it. So we have our Discord API availability graph. As is traditional, we measure it by percentage of 200 level HTTP requests against the total number of HTTP requests. And we can see here it drops immediately to about 25%. We use Discord in our day-to-day work, and we could tell pretty much immediately something was very wrong. So we immediately started incident response and okay, well, what could this possibly be? Which leads us to tip number 2. Correlation doesn't imply causation, but it can put a giant spotlight on it. They taught me in elementary science, correlation doesn't imply causation, but when operating distributed systems, it pretty strongly hints at it, right? So we have this really helpful graph in our monitoring that we use during incidents. It's called relative time spent in downstream services. It's based off of APM traces that tell us how much time is being relatively spent in downstream services, such as auth, So we can see authentication here. It's the big purple spike. It's telling us, hey, something's very, very wrong with auth. So while we're discovering this, the automation has drained zone C and stopped the nodes. So at this point, we're signed up for that RAID rebuild, but hopefully we can recover the system before that 45 minutes elapses. So at this point, we see an issue with authentication. Our authentication alarms are going off. It's time to look at the database. So we look at the database and it looks pretty unhappy, but what does an unhappy ScyllaDB look like? Well, you'll see failing read queries, which is something we saw. We typically want reads to be successful and not fail. So failing read queries is a sign of a problem. Additionally, we saw spikes in background reads. So background reads, things like updating materialized views, replication. Seeing spikes in those is an indication that things aren't working the way we intend them to. And lastly, latency. Latency is always a great metric, right? To determine how well your cluster is behaving. If queries are fast, it's a great sign. I've linked our latency graph here. It's not fast. It's very much skyrocketing. Our latency graphs typically do not look like that. So the ScyllaDB authentication is very much not happy. So what can we do? We want to recover it. Well, that leads us to tip number 3. Failure often isn't all or nothing. Recovery doesn't have to be either. Operating distributed systems, right? Graceful failure and partial failure are systems that are scenarios you should be comfortable with and familiar with. Recovery can also be partial as well. So at Discord, priority number 1 for us is mitigation. How can we get users back online, restore traffic and functionality to the platform? So I've linked the API availability graph here again. It's not great. We want it better. Whenever we have an overloaded system, such as our ScyllaDB here, I like to think of it as an economics problem. I don't like economics that much, but this framing has always made sense to me. It's supply and demand. You can either reduce demand or increase supply. So increasing supply here is bringing Zone C back online, which we can't really do because at this point we're about 40 minutes away from the RAID rebuild completing. So we need to reduce demand. Well, how can we do that? We can choose to drop less critical traffic to help the system recover. So at Discord, when I type a message, you might see, Bo is typing. Helpful message, but not critical. Prime candidate to drop during an incident. So we drop some less critical traffic and we can actually see the graphic somewhat recover, not to 100%, but it gets better. It's not enough though. We measure availability right in terms of 9s, not 6s. 65-ish% is not great. So we've already used our biggest tool here to reduce demand via load shedding, but we want more recovery. So what can we do? Well, we talk about it as a team and we're looking at the data and we say, well, our metrics tell us that about 50% of our users are back online. And 50% is also the number that would be implied if one troublesome node in our authentication cluster was down and one was up in a zone, since we run 2 nodes in each zone. Okay, well, what if we restarted a node to clear out a query backlog to help recovery? It's interesting, but there's a big risk with that. If one zone is down, if we restart the healthy node and not the degraded one, we'll have completely lost our quorum consistency and be 100% down. That's not what we want. You don't want to coin flip during an incident, cut the red wire, cut the blue wire. Which leads us to tip number 4. Teamwork makes the dream work. Don't firefight alone. Having a team full of people there to help out, gives you so much power. You can discuss things, discuss pros and cons, investigate different paths, parallelize work. It's super helpful. So as a team, we're discussing this. We're like, okay, what can we do? Well, the big question we come up with is what information would we need to make this operation safe? To do it and recover versus be 100% down. Like, okay, well, let's find something that tells us definitively what the affected node is. So it's time for tip number 5. Sometimes you go on a side quest. Also, recovery isn't linear. It's not a linear path sometimes. So we see a message that implies that our authentication service is having issues connecting to the database because of bad credentials. And so we're investigating that and checking system auth, key space, replication settings, making sure that we didn't accidentally break that. At the end of the day, it was a red herring error message. We parsed an error message in our application slightly wrong. Sometimes you go on a side quest. But as we're investigating, we see it. The great clue. The logs tell us that Scylla is having issues connecting to the B nodes only. The D nodes themselves are fine. Well, Only connection errors to B is pretty interesting. If the cluster was overloaded, I would expect both B and D to be overwhelmed, but seeing errors connecting to only B is very curious. And then we recall the slow RAID rebuild. Well, B2 took twice as long to rebuild. That's very suspicious. And we're having errors connecting to B. That sounds an awful lot like a degraded disk. So we think, okay, we can restart B2. But at this point, there's about 5 minutes to go on the RAID rebuild. So we're like, okay, 5 minutes to go. We can wait. It'll be a little safer. So 5 minutes later, 11:41 a.m., we recover. Zone C's nodes come back online, having finished their RAID rebuild. Now we're able to restart the B nodes, now that we won't lose Quorum, and we see full recovery. The API availability graph returns for the last time for you to look at the last part, the nice, pretty 100% straight line. Love that. Love when it stays that way. So we had this incident. There was a big availability loss, but why? What were the causes of this? So after analysis, this is what happened. We had a degraded disk in B2. So we did some forensics, we did some analysis, and traced it down to a degraded local NVMe SSD. It's not ideal. But additionally, the cluster was under-provisioned. A degraded disk by itself shouldn't have caused an incident of this magnitude. We were down to like 25% availability. Even if we're running 2 nodes in each zone, we should have only been down to about 50%. So the cluster itself was under-provisioned. It couldn't handle the loss of Zone C and B2 being degraded. Additionally, there was a cold row cache. So Scylla maintains an in-memory row cache for all the reasons you run a cache, right? Speed, reducing disk access. In our period of downtime, we didn't actually wait for the cache to warm up. This wouldn't have solved the problem or completely prevented it, but it would have potentially lessened the initial impact if we had waited for the cache to warm up. And lastly, this one is very much our fault. Our application to better mitigate maybe ephemeral authentication requests will retry errors to our authentication, server errors to our authentication service. And so we had a self-induced retry storm. So the database gets overloaded and we're like, hey, do you want some more requests? Retry storms, they're very fun. So it leads us to tip number 6. Always learn something from an incident, right? We had this incident, it took a while, it was not great, big downtime. That's a tremendous learning opportunity for us, right? A system behaves in an unexpected way. We have a chance to learn more things about it and improve it. So always learn something from an incident. What were our takeaways? What do we want to share today? Degraded disks don't always immediately cause problems. I mean, you tend to think of it like, oh, there's a degraded disk. Things are suddenly very bad. But actually, we were fine to start with. When B, C, and D were all online, with latency-aware routing, we were good. We were able to handle it. We had full capacity in the cluster. We were able to shoulder that blow. But when we dropped down to 2/3 capacity, the cluster was unable to keep up. So degraded disks, this slightly degraded condition where we can operate normally, but when we're performing operations, it might break things. It's something we very much want to avoid. And so we added further disk health checking to catch this. Our Scylla startup scripts do some disk benchmarking at the end to make sure that everything is good. But the big takeaway for me is really this one. Consider the impact of quorum loss when designing cluster topologies. So we lost quorum. It can happen. It will happen, but it doesn't need to be this costly. We lost over half our traffic. Are you okay with losing 1/n of your traffic to the cluster if you lose quorum? Where n is the number of nodes you run? What happens to your upstream systems? What value of n are you comfortable with? Encourage you to really think through the impact of quorum loss when designing cluster topologies. It doesn't mean add a bunch more nodes and spend a ton of money. You can also do it in a cost-neutral way, where potentially you run more smaller nodes instead of fewer larger ones. So I promised 7 tips for Scylla Sev success, and sprinkled through here have been those 7 tips, but why not sum it up at the end with them, right? Losing quorum should be avoided at all costs, but it happens, and you should be prepared for it when it does. Correlation when performing operations doesn't imply causation, but it can put a giant spotlight on it. Failure isn't all or nothing, especially in distributed systems. Recovery doesn't have to be either. Always strive towards mitigation. Lastly, teamwork makes the dream work. Working together with a team You'll get to a better outcome. You'll get to share work. You'll get to discuss problems. It's honestly my favorite saying. My wife is tired of me saying it. Sometimes you go on a side quest. Recovery isn't linear. It's not all or nothing. Sometimes you chase down a lead and an incident ends up being completely wrong, but that's okay. Always learn something from an incident. Your system has told you how it performs in a way that wasn't expected by you. Always learn something. Use that to improve it. And consider the impact of quorum loss when designing cluster topologies. Do you want to lose half the traffic to your cluster because you're only running 2 nodes? Consider what will happen in your very anomalous cases when designing cluster topologies. Well, thank y'all for your time today. I'm at Voluptuous on Twitter and Something Complicated on LinkedIn. Not actually something complicated, just a long URL we've got linked here in the slides. And lastly, don't forget about my book. I'd love for you to buy it, especially if you enjoyed the content today. It's designed to help you handle incidents like this in ScyllaDB and learn what it's doing under the hood. We've got the discount code here. Go to manning.com for 45% off. Thank you for your time, and I'm excited to see the rest of the talks this week. Thanks, y'all.